It's a pleasure to have Will Donnelly from Fermion Institute, and he's going to talk to us about string entanglement and large N expansion to GEH theory.
All right. So thanks very much for the invitation. Happy Super Tuesday, everyone. I'm going to talk about a series of works, a couple of papers in collaboration with Gabriel Wang, and some results produced this past year in collaboration with two undergraduate summer students, Sydney Timmerman and Nico Valdez. And the goal of all of this is to try to understand something about entanglement in string theory and what it has to do with large N gauge theory, and to explore these difficult issues in a toy model where we can actually do some calculations and understand things. Okay. So the big picture is that there's evidence for a deep connection between gravity on one side, classical geometry, and entanglement on the other. And the object that plays a central role in all of these discussions is what we call the generalized entropy, which is the sum of the famous Bekenstein-Hawking entropy, A over 4G, and the entropy of whatever quantum fields are in your theory, say outside of a horizon. Okay. This term S out, I'll be considering the case of pure states where it's really an entanglement entropy of quantum fields. Okay. And so in holography, this object is captured by entanglement entropy of a dual conformal field theory that lives, say, on the ADS boundary. And that has some parameter which will, okay, so we'll call a large N. It's not always a large N gauge theory, but that's the context in which I'm going to think about it. So at least in some instances of the correspondence, you have a gauge theory with a gauge group, UN or SUN, with a large, where N is very large. And you expand the entanglement entropy and the 't Hooft large N expansion, and you see something like this, where this classical Bekenstein-Hawking-like term, or the Ryutaki-Yanagi term, comes at order n squared. And one can argue that the subleading corrections are capturing this bulk entropy term, and those appear at order n to the 0. And there are further corrections, which won't be important for this talk. The important thing that I want to understand about this is that the area term and the entropy are really one object. They're really they're unified in some sense. It doesn't make sense to talk about one without the other, and that's kind of the key insight. And it's why you would say that, well, part of why you would say there's some connection between geometry and entanglement. In some sense, the theory likes to put those two things together. Please feel free to interrupt and ask lots of questions. This is just, for now, it's just motivation. Okay. Now, why would you put those things together? Well, the bulk theory is not. So we often think of it as being either a classical gravity theory or maybe with some perturbations, but ultimately we believe it's a string theory. And there's this old argument due to Lenny Susskind that strings naturally can count this 1 over G type of term. So why is that? Well, suppose we think about calculating an entanglement entropy in string theory. So we take a Euclidean, we think of the partition function of string theory as a sum over all connected Euclidean world sheets. And the way that you do this calculation is you insert some defect into the Euclidean path integral along a codimension 2 surface. So here I'm drawing a 3-dimensional Euclidean spacetime that's like the 3-dimensional space, and I've put in this codimension 2 defect here. It's just this line. And I introduce some non-trivial angle around that. That's some beta that's not equal to 2 pi. And there's some procedure for differentiating the partition function with respect to that beta. So in the end, what you find is that only those world sheets which intersect the entangling surface or which encircle it contribute. So that sort of explains why there's something like an area law instead of a volume law. Yes?
This is a target space picture?
This is a target space picture. That's right. So this is like a sphere world sheet embedded into target space, a torus. You'd have also a two-handled torus, and so on.
Three-dimensional target space in this picture.
That's right.
One of these dimensions is time, and so the line is like this entangling surface.
Yeah, that's right. That's right. It's all Euclidean. But yes, one of them should be thought of as time. So you could think of like out of the screen as time, and this way as the other directions as space, for example. You have one space, a space direction along the entangling surface and one normal to it. Yeah. So what you can show is that, so first of all, that only diagrams which intersect or encircle the entangling surface contribute. But the thing that string theory has that field theory doesn't have is a sphere diagram. So this, if you take a sort of field theory limit, what will happen is this will just contract to a point, and you'll think of it as just a local classical counterterm. But in string theory, this is actually a dynamical object. It's something you can calculate. And if you just look at how at its scaling with the string coupling, it comes with a g string to the -2, which is the sort of 1 over g type of scaling that you expect from a Bekenstein-Hawking entropy. Or in holographic language, that would be like the n squared term. So the observation, so it's this picture, as far as I know, has never been made rigorously precise. The problem is you have to take the string theory off shell, and that's a very difficult thing to do. But it was
the unique new thing that strings add to this picture is that a single string could be divided by the entangled surface.
That's right. That's right. Whereas if you take a particle-like limit, you can't cut a particle. Yeah. And that's basically the key thing that strings bring, and that'll be an important. That'll be important for sure. Okay. And yes, so you can actually give a statistical interpretation in terms of this thing. If you slice in what I'll call entanglement time, meaning if you take an angle that's where this is the origin and kind of slice it going around, what this thing will look like is it'll look like an open string with two endpoints sitting on the entangling surface, and it'll kind of sweep out some path and then and come back to itself. So if we want to interpret this as a sort of in this way as a sort of modular flow, we have to think of this as an open string diagram, and it's anchored to it's anchored to the entangling surface, and in that sense, we can think of the entangling surface as a kind of brane. Okay, so that's the picture that Lenny tells us. Okay, but then we'd like to understand this sort of more canonically as as a counting of states. So on the gauge theory side, there's something similar that happens. In the gauge theory, we have a Hilbert space that doesn't factorize according to local regions of space. So often when we're thinking about entanglement, we think about lattice models where you have some local set of sites, and there it's very natural to choose some subset of the sites and take the tensor product of some subset with some other subset. Yeah. But in a gauge theory, it doesn't really work that way because of constraints. Instead, there's a different way to think about entanglement where you can associate Hilbert spaces to regions, but now what happens is that the Wilson loops of the theory, which you can kind of think of as string-like, they're string-like objects, can cross the boundary, and you have to ask the question of how you split one of these up. Now, what happens is that you can take a Wilson loop and you can cut it into two Wilson lines, but then the endpoints transform in some non-trivial representation of the gauge group. And there's still a very natural notion of entanglement entropy associated with this, and it takes the following form. So R is every possible representation of the gauge group on the boundary that your states can transform in. There are three parts. One of them So first of all, you could just have some sort of entanglement entropy within a fixed R sector. So you could just have some, say, local gauge invariant excitations on the interior entangled with some local gauge invariant excitations on the other side. But then there's some piece that's associated with the fact that the representation that you're in can fluctuate in some given state. And there's some classical Shannon entropy associated with that. That's this term in the middle. And then finally, if you have higher dimensional representations, when you cut the Wilson loop into Wilson lines, there's some additional degrees of freedom living at the endpoints. And those are in a maximally entangled state. And you wind up with the expectation value of this local operator. Yeah.
So you only consider Wilson loop?
Pardon?
You only consider Wilson loop?
So this thing is true at the level of any state of, say, a lattice gauge theory.
So you can put some charge inside.
There can be charges inside. There can be, yeah,
and
that's right.
It's a total representation of Q.
Yes, it's a total representation, meaning it's a representation of the product of the gauge group at every length that intersects. That's right. In the case that I'll consider, it'll be much simpler because I'm going to go to 2 dimensions. But this is the sort of general version of it. That's right. And there won't be any matter. Yeah. OK. But one can make the following observation, that there's a piece of this formula that's local and just takes the form of an expectation value on the entangling surface. And that looks kind of like this Ryu-Takeyanagi or Bekenstein-Hawking area term. It's the expectation value of some local operator. And so, so one might ask if these two things are related. Okay. Good. So, okay, so here are the two main sort of big picture questions I want to attack. One of them is, first of all, what is entanglement entropy in string theory? Given that the fundamental degrees of freedom are extended objects. Yes?
Why is dimension R is a local operator if it's not the Wilson line, which is cutting off?
Ah, good.
Wilson line cutting off is, of course, yes, probably, very probably small, so it's just essentially area operator.
Yes.
But if you can put any charge or something, R is a reducible representation of whole.
Yes, so good. So if you want to ask which representation these things are in. So in a lattice gauge theory, it's really just like having a lot of, I mean, really you can think of any state as being expanded in a basis of Wilson loops. And it's basically the thing that would, it's basically the object that would measure the representation of the Wilson loop. So it's constructed out of the non-abelian electric field.
Anything inside is singlet mostly, and then something is cutting the boundaries.
That's right. It cuts at the boundary, and that's why it's local to the boundary. Yes. Yeah. So it's crucial that really what you're doing this cutting in a geometrically local way. It's right on the boundary. Yeah. Okay. Good. Good. So question 1 is, how do we understand entanglement in string theory, given that there are these extended objects? Roughly, how do we cut a closed string into open strings and then count, the pieces? Basically, the question. And then the second question is, why do we have this behavior that at leading order in n squared we have something like a classical local object? Why do we have this area term? In general, an entanglement entropy is not linear. It's not the expectation value of anything. It's nonlinear in this state, and it's not a local object. So we want to understand how this apparent locality emerges in the large n limit, and corrections to this sort of leading formula. Okay. So these are lofty goals, and so the way that we do this is we choose a much simpler model, okay. So the model that we're using is two-dimensional Yang-Mills theory, and it's this nice sweet spot where it's completely solvable. You can do all the calculations you would want to do, but it still has some interesting physics in it, some interesting sort of stringy physics. Okay. So the fact that this is exactly solvable is an old result. And so because of that, we can understand entanglement not only at finite n, but also we can understand something about the entanglement entropy in the large n limit. And then the other crucial thing is that there is a string theory description, a string theory dual of this. which applies at large n and any value of the of lambda, the 't coupling. Now, one thing that's special about this string theory is that it has no local degrees of freedom. So two-dimensional Yang-Mills is a quasi-topological theory. I'll explain what that means in just a moment. So the theory has no local degrees of freedom, but it has these we'll see it has these non-local winding type of modes. So really, in a sense, it allows us to focus in on the thing that's really unique to a string theory, which is the sort of extended objects. Okay. So now we can ask questions that sort of cut across this duality. We can ask about entanglement entropy in the gauge theory and ask what this corresponds to in the string description. Okay. Good. Okay, so here's an outline of the talk. Basically, there are. I'm going to describe two-dimensional. I'm going to start by describing the same system in. Well, I'm going to describe the same physical system in 3 different ways. So it's a. I don't know. Do you call it a triality? Or it's 2 dualities. I don't know. Okay. There are 3 descriptions. The first one is I'll just describe the calculation that one can do in two-dimensional Yang-Mills theory, the quantization of the theory, how one can talk about entanglement, and it'll be useful to phrase it in the language of topological quantum field theory. Okay. And then I'm going to give the string theory description first as a sum over this sort of sum over world sheets. And then in a canonical description, there's a way you can describe a canonical evolution of closed strings, and a canonical, and there's also an open string description and how they're related, and then how one calculates entanglement in this picture. And then third, I want to describe further duality to a fermionic model, and how that fermionic model is useful for doing actual calculations of the behavior of the entropy in the large n limit, and doing the 1 over n expansion of that result. And the main calculation that we should have in mind is basically the two-dimensional de Sitter entropy. So what we'll do is produce, so you'll have something like the sphere diagram. You can start with the Euclidean path integral, prepare a state here, which we can call, say, the Hartle-Hawking state. And that defines, so by doing the path integral on a hemisphere, one obtains a state that lives on the equator. We can then cut this state into 2 pieces, say here and here, and describe it as a state as an entangled state of 2 halves of the circle. So that's the sort of prototypical calculation that one can do in all 3 of these descriptions. One can also consider more general things, of course. You can put handles on here, and you can cut this in more places, but the most basic version is just this. And the key thing is that there are 2 ways to view this calculation. You can either, so you can when you close this up, you can either slice it in a sort of closed channel, or you can slice it in an open channel. And perhaps the main message is that the open channel is really essential in order to see what the state counting is doing. You can do all the calculations here, but you won't really learn much about what is being counted. And here you see what's being counted. Okay, so here's two-dimensional Yang-Mills theory. It's got a familiar action of f squared. One thing, so I'm going to work to take the large n limit. We introduce the 't coupling lambda. g squared n. And here, unlike in 4 dimensions, it's dimensionful. It has units of length to the -2. And another thing that's unique in 2 dimensions is that this action is invariant under area-preserving diffeomorphisms. Okay. So it's almost it's in that sense almost a topological quantum field theory. A TQFT would be invariant under all diffeomorphisms. This one, because it's only area-preserving diffeomorphisms, we can still use many of the methods. There's just one thing that's going to change. Now the partition function, instead of being a topological invariant, can also depend on the total area of the Euclidean manifold. Yes?
Why is that last fact special to 2D?
The invariance under...
Yeah.
It's because F is a 2 form, which is a top form, and so you can dualize it to a scalar, and you can rewrite this action as basically just square root of g times a scalar squared. And then you see that, so if you looked at it this way, you might think, well, there's lots of there are metrics here contracting these things, but really that's an illusion. They're really just square root of g. Yeah. Okay, good. And you can kind of see that, okay, you can kind of see that that's never going to happen in higher dimensions because the theory has local degrees of freedom, which will propagate along a light cone. So it shouldn't be invariant under such a large group of symmetries. It's not anything like a topological theory when you have photons, okay, or gluons, I guess. Yeah, good. Okay, so here's a canonical description of this sort of closed sector of the theory on a circle. States are wave functionals of the Wilson loop around the circle. And gauge invariance imposes that they be class functions, namely that the wave function is invariant under conjugation by a group element G. Yeah. The canonical conjugate to U, in a sense, is the electric field, the non-abelian electric field E, and the Hamiltonian is just trace of E squared. Yeah. Good. Now one can actually directly diagonalize this object. It's diagonal in a basis of wave functions, which are of this form. So they're labeled by irreducible representations of the gauge group. So you can build a functional just by taking whatever group element your holonomy is, mapping it into some representation, and taking the trace. And the eigenvalues of the Hamiltonian are the quadratic Casimirs of those representations. Okay. So simple enough, and this R basis is extremely useful for doing calculations because obviously it diagonalizes the Hamiltonian. Okay. So that describes evolution along a cylinder. In order to describe things like this Hartle-Hawking state, we'd like to do more general things than the cylinder. We'd like to talk about amplitudes on general Riemann surfaces. And we can do that by building up the partition function from building blocks. And this is very much in the spirit of what one does in a TQFT. So I can describe all of these fundamental building blocks in this representation basis. So the cylinder is just the e to the minus h evolution, as we saw in the previous slide. The new thing that one needs is something which is topologically a disk. And what you get by putting, basically from putting a boundary condition at the, you can think of it as putting a boundary condition sort of at the pole here, that the holonomy is trivial. One gets an extra factor of the dimension of the representation. So this produces a state. And then one also has a pair of pants where you have an amplitude like this. It turns one copy of R into two copies of R, and there's a factor of 1 over to the dimension here. And in fact, you can see that, well, once you know one of these, you know the other, because you have to be able to sew this cap onto one leg of the pants in order to get a cylinder. Okay.
So why the pants is like R and one dimension R?
Good.
It must be secret or
yeah, so the reason why the label R is the same on all on all three boundaries is because this R is determined by the electric field, the non-abelian electric field, and the non-abelian electric field is constant here. So it's covariantly constant. So any invariant you construct is constant over space-time, which means that it's the same here and here and here. So, and once you know that all the invariants of E are the same, you know that the representation matches. The reason for why 1 over the dimension of R, I think, it's maybe a little less clear, but what you do is you expand, what you wind up doing is you expand a delta function of U in this R basis. And you just see that their dimension are factors. Yeah, we'll see that these actually have a very natural interpretation in terms of entanglement. Ultimately, what these factors wind up telling you is that in order to glue two Wilson lines together into a larger Wilson line, you have to insert a complete set of states, and you have to sum over them. And so there's a normalization factor associated with that, which is, it's like you have a maximally entangled state of n things, and so you have a 1 over square root of n. That's really all it is. Yeah. Okay. Okay. And from those basic building blocks, you can get the partition function of any surface. So for a surface of area A, an Euler characteristic chi, which is 2 minus twice the genus, you just get the following answer. So it's a sum over all irreducible representations. Depends on the dimension of the representation and its quadratic Casimir. Depends on the Euler characteristic and the area of the manifold. Okay. And in fact, that fact alone is sufficient to calculate entanglement entropy via the replica trick. You can just take this manifold, you can cut it along some set of points, make n copies and identify them in some way. That's going to be a Riemann surface of some Euler characteristic and area, and one can just calculate. That's true. Yes, and that fact is very important in conformal field theory. And in this case, it winds up not being important, and the reason is basically because of the area-preserving diffeomorphism invariance. You can smooth out all those singularities. Yeah. That's one of the things that makes this much simpler than the CFT case. Okay, good. Okay, someone can do this calculation, but I think it's more instructive to do something that will tell us about the state counting interpretation. And in order to do that, we need to think about the Hilbert space of a circle in terms of Hilbert spaces associated to intervals. Yeah.
I guess as a follow-up to John's question, the fact that it does these area-preserving diffeomorphisms set, how specialized is that to, I guess, the low-dimensional case? Because if it's very specialized to the low-dimensional case, then we try to extend these lessons to higher-dimensional Yang mills or super Yang mills that maybe we would be interested in doing. I'd be a little concerned about extensibility in that direction if you focus on a property that seems somewhat fatal in the CFTs.
Yeah, no, I mean, I agree that's a concern. I mean, I think that's right. In a CFT, you have to be, it's much more, you have to be much more careful about exactly what boundary conditions you put at the entangling cut. But I think, my feeling is that the lesson's really about the large n limit and about the string expansion, and I don't think those aspects are really, they don't really care too much about the fact that it's a TQFT. But I think the general fact that will generalize is that you want to put some boundary condition on this cut that is in some sense innocuous, that you can sort of take this point to be very small, and that And that's just like you never put a boundary there to begin with. But yeah.
But did it use one of these area preserving isomorphisms to remove the canonical defect? Did you have some kind of non-contractible circle around the branch point?
I don't know whether you should probably you should count it as it's a question of whether you count that as non-contract. Yeah. If you don't allow it to move through the singularity, then yes, there'd be some non-contractible cycle. And you could and then you might think, okay, if it's really singular, maybe you could put some different boundary condition on that circle. Maybe yeah.
In other words, does it affect your trivial holonomy boundary condition from before?
To put a conical singularity in general, probably it would in this theory. In this theory, that's still in some sense, the right boundary condition to put. Yeah. But yeah, and more generally, I think more generally, you'd really have to think about, okay, if I'm really doing something with a finite conical angle, what's the right boundary condition? But yeah. Good. Okay, so the point is now we want to have a canonical description not only of circles but of intervals. So let's consider Yuan-Yang-Mills theory on this strip geometry. Now states are still you can think of them as wave functionals of this Wilson line, but now it's a line, not a loop, and you don't impose the sort of gauge invariance at that extra endpoint. They're just arbitrary functionals. The Hamiltonian's the same, is still trace of E squared, but what's different is because you didn't impose that, because there isn't that other gauge invariance condition, there are these extra states living at the endpoint. And so I can still label them by a representation, which is the eigenvalue of this H, but now I have these degrees of freedom at the endpoints, and these are transforming in the states transforming in the representation R. Okay, and one can do the same kind of a TQFT like game. You can associate amplitudes to strips, these sort of open caps, and these sort of open pairs of pants. And they satisfy a similar set of axioms of what's called a symmetric Frobenius algebra. Okay. Good, and they basically just say whenever there's a diagram that you can cut up two different ways, that those define the equivalent objects. Okay. Okay, but now we need more. So we have a sort of closed TQFT and an open TQFT that we could define. But what we'd like to be able to do is we'd like to be able to take our circle and we'd like to be able to cut it at some point and unwrap it into an interval. So we want to have some map from the closed Hilbert space into the open Hilbert space. And moreover, we'd like to be able to take some interval and cut it as well into two intervals, which would be some map from the open Hilbert space into two copies of the open Hilbert space. Okay. So the first thing we can draw something like this. In the TQFT literature, it's sometimes called the zipper. You sort of unzip the circle. Okay, and that's given by the following map, which takes this state R labeled by a representation, and it turns it into. It introduces these degrees of freedom at the endpoints and puts them in this maximally entangled state as it's written here. And then the thing that turns a single interval into two, in fact, we already have this as open coproduct, this open pair of pants type diagram. Okay. And this structure, so now that I've added this zipper, I have a whole new set of conditions I want to satisfy. I have what's called a knowledgeable Frobenius algebra, which is the closed sector, the open sector, and a bunch of rules that connect them. Okay. And the rules, the rules are as are these ones. So maybe I won't describe these in detail, but they just come from. You could maybe convince yourself that these things are true just by looking at the diagrams and seeing that there's some deformation I could do to turn one into the other. I can take this line and just pull it up, and those two things are topologically equivalent. The non-trivial thing is that this is a minimal set of things that you can assume from which you can derive any other things. Okay. And the one that maybe will be interesting for us is this last one, this Carty axiom, where you relate, so-called because it relates something that's an open channel kind of diagram to a closed channel diagram. And that'll be essential for us. Okay. Okay, and in fact, we need one additional property, which is a property of our boundary condition. So remember, we were saying we wanted to be able to sort of poke a little when we cut our partition function. We want to be able to sort of think about inserting cutting out a small disk or something, on which we put some innocuous boundary condition, meaning we could just close it back up again without penalty. Okay, so you can encode that with this one additional thing which you can take as an axiom. It turns out to be, it's true for the rules that I gave you for two-dimensional Yang-Mills theory. And from this one, it follows that you can sew up holes. Using the other axioms, you can show that you can sew up holes anywhere that they appear. So if you have this kind of window-like thing, you can close it up, or you can have a hole in the middle of a diagram like this and close it up like that. It's just the statement that introducing an entangling surface shouldn't change the state, shouldn't change any correlation functions or anything. Okay, so now with all this machinery, we can do something like the simple calculation of entanglement of the de Sitter vacuum state. Okay. So the de Sitter, the Hartle-Hawking state is this hemisphere diagram. So how do I think of it as an entangled state? Where first I have to cut it open into, think of it as an interval, and then I cut that interval open in two. So now I think of this state of the circle as a state of two intervals. Okay, using the axioms, I can just rewrite that as this sort of macaroni type of diagram. Or, yeah. Okay. And that corresponds to this entangled state, where here I have indices A. So I'd have some representation R, which is the same on both sides. I'd have some index A and B on the left. And then just following the lines, I see that has to correspond to indices B and A on the other side. Okay. But what's nice about this is I can also, I can now, if I construct a sphere partition function like this, I can now view it in a different channel. I can view it as a trace in the open channel. And it's just a trace of this, of the sort of open sector Hamiltonian, which is just this C2 operator. Okay. So it's a sum over all representations. But this open trace now includes a sum over the indices that propagate along the left and right boundaries. And while these two diagrams calculate the same thing, the right one, the fact that you can write it as a trace is essential to have some interpretation as a statistical partition function, and therefore as a statistical entropy. So from this, one can get very easily the entanglement entropy, and it's given by this same formula or a special case of this formula that I showed early on. It's given by an ordinary statistical entropy, a Shannon entropy of the fluctuating representations, and there's this factor twice the log of the dimension, which comes from this sum on the endpoints. And this is in precise agreement with what you would get from the replica trick. In the replica trick, it's the way you get this other term, it comes from the fact that it came from, in the partition function, there is some factor dimension of R to the power of chi. Whereas here, the statistical meaning of that thing is clear. It comes from entanglement of these extra indices that you have to put to cut the Wilson loop.
Was 2 there?
Pardon?
Was 2 there in the previous formula? 2
Oh, 2. Good. It wasn't, but that's because I cheated a little bit. And the thing I had R was one copy of the group for every endpoint, and here there are 2 endpoints. Yeah. if you like in the replica trick, it comes about because that 2 comes from the chi, and chi is 2 for the sphere. Yeah. Okay. But yeah, in general, okay, good. In general, you could try cutting at m points here. See, okay, there's m is 6, and then you'd have just an m log mr. So, yeah. So this term winds up being sort of extensive. It scales with the number of cuts. Okay, so that's the description of the two-dimensional Yang-Mills theory. And now I'm going to show how that same calculation comes about in the string description. Yeah?
Can you go back one slide?
Yes.
So I'm trying to understand if this is a big deal or if it's not a big deal, but the fact that your entanglement entropy is proportional to a Shannon entropy, which in general, well, in some certain cases can dominate over the second piece. Is there some significance that I should assign to that? Because generally when the entanglement entropy is purely Shannon, then there are interesting things that happen when I'm interested in describing like channel capacities associated with that particular entanglement quantum channel. Like for example, when the Olivo quantity is exactly the Shannon entropy, that's a situation that gives you perfect distinguishability. I'm not saying this is exactly that, but should I think about situations where the first term dominates over the second one? Be particularly interesting, or is that just another thing?
I don't know if those are interesting. I do, well, okay. I mean, what we'll see is that holographically, it's really or in the large N limit, it's really the second term that dominates. So, are there interests? Yeah, in some sense, those from a kind of holography-inspired point of view, those would be interesting because they'd be sort of very quantum cases where kind of the quantum piece was dominating over the expected classical piece. They're kind of very non-classical states or something,
yeah, so those
in some sense, but I don't know how to.
correspond to the situations that Newton's down here right now has talked about recently.
Okay.
The entanglement entropy is dominated by the squashed entanglement,
Okay.
which is the non-classical portion of the entanglement. So
Okay.
it could be that that's what you're seeing, or that's an interpretation.
Okay, that sounds interesting. You'll have to tell me more about it because I'm not really familiar with some of these results that you're talking about. Okay. Thanks. Yeah.
Is there some easy way to see that it's extensive? Like, what's the genus of the thing that you compute for like m endpoints?
Oh, you mean from the replica trick? Why do you see that it's proportional to?
Why is it extensive?
Why is it extensive? I mean, I'll get to that eventually. So maybe remind me. There's going to, yeah. If I get there. Okay. So good. So now I want to talk about the string theory description of this same calculation. Okay. So the simplest thing that, well, I don't know if you want to call it simple. Okay. The first thing that Gross and Taylor did was really work at the level of the partition function and show that the Yang-Mills partition function could be written as a string-like like path integral. So what they showed is if you take the Yang-Mills partition, the two-dimensional Yang-Mills partition function at large n, you could rewrite it as a sum over maps from a world sheet sigma into a target space M. Those maps are branched covers with I branch points. So you sum over the different possible numbers of branch points, and you integrate over the locations of these branch points. And the weight in the path integral, you get this factor of 1 over n to the minus the Euler characteristic of the world sheet, which is a characteristic of string theory. Basically, you have the genus expansion with a string coupling given by 1 over n. There's some symmetry factors associated with each diagram. And then you have the Nambu-Goto term where you have e to the minus the area of the, so it's the induced area of the world sheet, and since it's an n-fold cover, that's n times the area of the spacetime. Okay. So there's a string coupling, 1 over n, and a string tension given by the 't Hooft coupling. And that just gives you can check that this gives the partition function as a power series in the 1 over n expansion. Okay. you can see where this comes from the canonical theory. So you can write a canonical theory of closed strings where you start from, say, a vacuum state, which is just a constant wave function, and you act on it with operators like trace of u to the k or trace u dagger to the k. And you think of trace of u to the k as creating a string that winds k times. These are oriented strings, so trace of u dagger to the k will create a string oriented the opposite way. And a general such state you can label with a permutation sigma, where the winding numbers are just the cycle lengths of the permutation. So the way you think of this permutation is you start by labeling all your strings, you follow them as you go around the circle, and they come back to themselves permuted in some way. And you can write the Yang-Mills Hamiltonian, and you see it has a term that just counts n, so n is the number of strings, tension times length, so it's got a Nambu-Goto type term, but it's got an interaction with strength. The strength of the interaction is 1 over n, like that's the coupling. And all it does is it takes two strings that are sort of on top of each other, it cuts them and re-glues them with a twist here. Okay. And then in space-time, what does that look like? Well, it looks like one of these interaction branch points. You start with, think about reading it sort of this way. You have two strings on top of each other, they go through this point, and now they're swapped. Now, once again, the cylinder is not enough. You need also something like, if you want to talk about the partition function on an arbitrary Riemann surface, you need to include something like the cap. Yeah. And something which is topologically a disk, and that requires something that Gross and Taylor called an omega point. And it has some sort of funny rules associated with it. Your strings can end in an arbitrary permutation, and anytime it does so, you get a factor of n to the power of the number of cycles. You can also merge strings with opposite orientations at the point, so you can kind of have it come in and reflect. And every time you do that, you get a factor of -1. And these omega points, you just have to put them in, and you hold their positions fixed. They're not integrated over like the interactions. Okay. And you have to put one every time you have a disk. Anytime you have a pair of pants, you have to put in a corresponding object, which you call an omega inverse point, whose rules are similar. Okay. But this was sort of read off. Gross and Taylor sort of read this off just from looking at the partition function and seeing what you had to do. But it's not, I have to say, I don't find this very intuitive. When you put this state here, the fact that you have these n enhancements means that actually this corresponds to a highly non-trivial excited state of the string theory. It's very far from being something like the vacuum. Okay. So where does this come from? Okay. Well, we'll see it's a lot more intuitive in the open channel. So there's this closed string way of slicing the sphere partition function, where it looks like an amplitude between one of these omega states. You insert an omega state, evolve it, and take the overlap with another omega state. But there should be some picture where we instead do the open slicing. Okay. And that's the natural one in order to describe entanglement. Okay. So now we want to talk about open string states. So just like we would act with trace of u in the closed string, here we can act with operators uij, which are like matrix elements of the group. And we should think of uij as creating a positively oriented string with some Chan-Payton indices at the endpoints. So you can think of it as anchored to some stack of n branes. Okay. And then u dagger just creates the opposite orientation string. Okay. And in general, to describe an open string state, I'll just give you a list of all the Chan-Payton indices of the strings going one way, and then a list of all the ones going the other way, which I'll call ij for, and then k I'll forget. Yeah. There's one additional subtlety, which is that these two sectors in the open string don't decouple because of, basically you can write a series of identities which are basically just u dagger equals 1. And that says that if I create a particular, creating a particular state where I excite strings going right and left is equivalent to not exciting anything. Okay. Good. So that describes the open Hilbert space. And now if we want to talk about entanglement, we further have to be able to embed the closed Hilbert space into the open and the open into two copies of itself. But those maps actually take a very simple form. If I have some collection of strings winding around, described by some permutation sigma, when I cut it open, all that I find is that the right Chan-Payton indices are related to the left ones by some permutation, by that permutation that defined my closed string state. And the open coproduct is even simpler. If I just have some indices I on the left and j on the right, I just insert a complete set in between. And what this allows me to do is if I take any closed string state, I can describe it now as an entangled state of open strings. So this is the rule that tells me just how to cut open my closed strings. Okay. And now the result is that I can take my sphere partition function and write it in an open channel, just as I did for the Yang-Mills theory. And now the entanglement entropy is counting these open string states, and they're ending on this brane-like object, which we call an entanglement brane. It's the brane associated to the boundary condition that you put at the entangling surface. And the modular Hamiltonian is just the generator of, well, if you like, de Sitter boosts, but in the Euclidean, they're just rotations that hold the entangling surface fixed. And this trace, just like it included in the Yang-Mills case, a sum over these representation indices. Now we sum over these Chan-Payton indices of the open strings. Okay. And moreover, this explains these funny rules of the omega point. In the open string channel, they come about for a very natural reason. Yes?
Even minus H open?
Yes.
H open goes bigger as the representation goes bigger?
Yes, that's right. Yes.
Dominated by small representation.
Ah, good. This is an extremely important point, which I'm going to get to right after I say what the. Okay, it's true that H open will suppress. It has the Nambo-Goto term, which suppresses more strings. Bigger. So in the string language, a bigger representation means more strings. So it does. The H does suppress those states, but there's also an enhancement, which we'll see. Okay. So they fight. Yeah. Good. So so what I want to say is when you have this open channel, it actually naturally explains the rules of the omega point. So this factor of n to the number of cycles, all that's doing is it's summing over the different Chan-Payton indices. Anytime you have an open string, the more strings you have ending on this thing, the more possible Chan-Payton indices there are. And you get factors of n, basically for every string. This factor of -1, where you had two strings coming with opposite orientations, in fact, winds up expressing the non-independence of the left and right moving sectors. What it winds up being is this identity that u dagger equals 1. And so from the sort of statistics of open strings, of bosonic open strings, you derive the rules of the omega point. Okay. Good. And now your question. Okay. So why are the rules at this brane important? And the answer is every time you think of adding a string to your system, it's true you increase the energy, so you get some suppression, but you also get some enhancement because now you have, it's like if you're maximizing the free energy, you gain energy, but you also gain in entropy. and there's actually some balance. And what it turns out is that the dominant states actually have order n squared strings in them. Okay. And that's where the sort of order n squared entropy comes from. So yeah, if you just looked at, you can sort of see, if you just looked at log of the dimension of R, if you had some state with a finite number of strings in it, that would only be growing like log n. How do you get n squared? Well, you actually it's because you add this additional sort of, I don't know, entropic force, if you like.
But it's not
tells you to have more.
Sense, right? Mathematically, maybe clearly the balancing, but what's going on? It's just
Yeah.
it's n squared.
Good. So, yeah. So in the string description, it's actually you can kind of see that this is what's going to happen. You can do it. For example, you can consider a theory where you truncate the interactions. So you can consider kind of like a free string theory and do these calculations, and you see n squared coming out very naturally. But indeed, the string. Okay. Thank you, because that motivates the next part of my talk, which is that the string theory is actually not the most efficient way to actually do calculations. And the reason is because you're creating this background which has some enormous number of strings in it. It's not like an ordinary perturbative calculation. And so if you wanted to actually work out the coefficients in the entropy, it wouldn't be a good way to do it. So that's why I want to talk about this. The last part of my talk will concern this fermionic model. Okay. Good. So why do we need yet another dual description? Well, okay, good. So as I was just saying, the string expansion is breaking down. It no longer converges. If you take and the reason is basically these the enhancements coming from these omega points can sort of cancel out the 1 over the suppression that you get from interactions. So you can have, at order n squared, you can have a sphere diagram that's, say, like an n-fold cover of the sphere with an arbitrary number of interactions. So now you have to, now you're really summing an infinite number of string diagrams to get these partition functions. It's a little bit reminiscent of what you might expect from the sort of Hagedorn behavior in the critical string, where if you have a high enough temperature, you can have holes in the world sheet that kind of proliferate. So you have it's like you have the interactions in this case kind of proliferate and break down. Your string world sheet, if you were thinking of it as some very smooth thing, it really isn't. It has a huge number of branch points in it. So in the critical string, what this means is that you're not expanding around a minimum of the potential. You have some mode that becomes unstable, and you have to find some new minimum for it. For us, this means we have to find some new, this new background, which from the point of view of the vacuum we started with, has some enormous number of excited strings in it. Okay. So now I want to describe what this Fermion model is. So it's natural to start to go back to the Yang-Mills theory and think about its states. So the natural basis was a basis of representations, and the irreducible representations of UN we can label by Young diagrams, which so we can think of some set of integer row lengths, n1 through nn, some non-increasing sequence. Okay. And we just do a simple change of variables. We write some positions of fermions, h, which are also integers, and now they're just going to be increasing. And so I can think of them as on a one-dimensional integer lattice. Yeah. And what's nice about this is that my Hamiltonian takes a very simple form. So if I think of these things as the locations of fermions, if I write the quadratic Casimir, that just is like an external potential for the fermions, where each, which is quadratic around the origin. And now this log dimension term So I can think of the dimension of r to some power as e to the log dimension, and think of it as an interaction potential. And what it is it's a logarithmic potential which is repulsive. Okay. You can think of it as a kind of entropic force. The farther away these things are, the more states there are. So it kind of pushes them apart, and it arises in a very similar way to eigenvalue repulsion in matrix models. Okay. And now the fermion, so the Yang-Mills partition function can be rewritten as this fermion partition function, where now I sum over all possible locations of n fermions, weighted by the sum of this confining quadratic potential and this logarithmic repulsion.
So what was the H in the previous slide?
H?
H1, H2.
That's right. So these are the locations of the fermions.
Yeah.
And they are related to the row lengths of the Young tableau by this formula. So
I is there. I is there.
I.
Because NI could be same. So.
That's right. The fact that these are different.
Yeah.
Yes. That's right. That's precisely why they're fermions. Yeah. Is because that's right. Well, I mean, the way to think about it is if you think about the difference in row lengths between two things, that's going to be that can be, that's some non-negative integer. And then if I add 1 to that, it's some positive integer, and that's going to be the gaps between the fermions. Okay. Good. Okay, so now I just have this very simple statistical model. I have n fermions on this one-dimensional lattice in a potential and with this repulsive force. Okay, good. And so that's a simple statistical model you can study. So here what I'm plotting is the density. You can take a sort of large n limit and look at a continuous density of fermions and see how it behaves. At low temperature and strong coupling, the external potential dominates. And it forces the fermions together into a kind of Fermi-C configuration. And this is the regime where the string description is good. The strings are little fluctuations about this Fermi-C. The left and the fact that you have left and right winding strings correspond to the fact that you have excitations of the left and right edges. Okay. As you raise the temperature, or equivalently lower the coupling, you hit this critical point where now the Fermi-C boils, if you like. It turns. You have just it goes away. There's a third order phase transition first studied by Douglas and Kazakov. And above that critical temperature, now the fermions behave very much like they were in a continuum. They sort of don't feel the fact that they're on a discrete lattice, and in fact, they form a Wigner semicircle distribution. Okay. So there, it's very much just like the random matrix, and here the string description breaks down completely. In fact, the 1/n expansion of the partition function in that phase has no perturbative 1/n corrections. There's nothing that you could interpret as a string diagram. Everything is exponential corrections. Okay. Good. Now the nice thing that the Fermion picture allows us to do is it tells us immediately how the different terms in the entropy scale. So I was saying that the total entropy scales as n squared, but now we can see how the individual terms behave. If you look at the log dimension of R, so remember that term was this pairwise logarithmic potential. And just the fact that it's pairwise, you're summing over pairs of fermions, and they're n fermions, you get an n squared scaling. The other term, what is it? Well, it's fluctuations of the fermion configuration, which is just the ordinary thermal entropy of the fermions in this potential. And so the entropy of n, it's the entropy of n fermions, and it scales like n. And you can confirm this with numerical simulations. And so here's a plot on the right, and the purple one is this log dim R term, and the other one is the Shannon entropy term. Okay. But this leads to a puzzle from the point of view of the string expansion, which is the following. we have an order n term in this entropy, and yet the closed string, the expansion, so it's a theory of closed strings, right? And the closed string theory is an expansion in even powers of n. So how can you get this? So it's true it's true we sort of introduce an open sector, but in the end I could have done the calculation purely in the closed sector. I can do the calculation just by writing, I should be able to just write the partition function of the closed string theory and take a replica trick and differentiate it. Okay. Indeed, these odd powers seem they seem very surprising, especially from a holographic point of view. Holographically, we thought that so we were sort of expecting an n squared scaling that corresponds to a 1 over g. But a linear in n scaling is like a 1 over square root of g Newton, or 1 over Planck length, not Planck length squared. Okay. So here's what's happening. So you might have thought in the replica trick, you could just expand the partition function sort of in a power series in 1 over n, and then just apply the replica trick sort of term by term. Okay. And here's why that doesn't work. So here's how you would do this calculation. You'd start by taking the partition function of a replicated manifold. So when you replicate, you get n times the area, and you get an Euler characteristic that's n times the Euler characteristic plus this correction. So I'm imagining you're replicating along m, you're cutting along m points of your entangling surface. Okay. And you can just check if you take the derivative of this expression using the chain rule, you get this. Okay. So you have an a derivative, but you also have a chi derivative that comes from the fact that you have to change the topology of the spacetime. Okay. And now when you change the topology, what are you doing? You're actually changing completely the counting. So this n scaling of the partition function, the powers that appear, the leading power is chi. So like the leading power of n is going to change as you change n. And you have to analytically continue across all of these topologies. And so the point is that in that procedure, I can't hold the power of n fixed as I do that analytic continuation. You can try, you get nonsensical results. You're like trying to analytically continue some function which is identically 0 beyond some point. Okay. So I think that, so the resolution is that in fact the replica trick doesn't commute with the genus expansion of string theory. Good. So I should say there's one exception to this argument. If m equals chi, I don't need to analytically continue. So that would be a case where that would be a sort of case where if the modular Hamiltonian is geometric, it's like some geometric flow, like in the case of de Sitter, I can just sort of continuously vary the replica index by just changing the area and not changing the Euler characteristic. Okay. So what happens in that case? Well, so good. So if m equals chi, there's basically only one case like this, and that's the de Sitter entropy, where chi equals m equals 2. And there, what you find is that indeed the Shannon entropy is order n, but it cancels precisely against a subleading term in this log of this log dim r. So the log dim r, although it's order n squared, also has a subleading term, and that's what's plotted here. So here's the Shannon entropy term in green, the subleading piece of the Boltzmann term, and they cancel pretty well. There's some numerical noise coming from the fact that we're extracting a subleading term in the large n expansion. It's consistent with 0. Okay. Good. Okay, so just to conclude, we saw that entanglement is very naturally expressed in this framework of open-closed TQFT. We needed to add to that formalism one extra axiom that's sort of characterizing this entanglement boundary condition that you can be shrunk to a point. In the string theory description, we saw that the entanglement is arising from the way you cut closed strings into open strings at this boundary, and that it acts very much like a brane, and we call it the entanglement brane. Okay. The n-squared scaling of the entanglement entropy arises essentially from these Chan-Payton indices of open strings that basically force you into these states of large numbers of excited strings. And it winds up having the form of the expectation value of a local operator, much like the Ryutaki-Yanagi formula. But then there's one surprise, which is that the subleading corrections are larger than expected. They're order n instead of order 1. So I think there are lots of potential areas of future work. One of them, the main thing is, okay, how much of these lessons can we carry forward to something like a critical string? Do we see the breakdown of the genus expansion that you expect when you do the replica trick? Do you see something like this cancellation between some subleading piece of the local term and an entanglement term? This can happen sometimes in field theory, that there's a contact in general there's some contact piece as well as an entanglement piece, and for certain field theories they cancel. It would be interesting if one could see that coming about somehow from the string expansion. And then if we consider non-geometric modular flows, can we see this cancellation not happen, and can we see some enhancement? That would be I think that would be big. It would be some stringy correction that's smaller than the leading classical piece, but still larger than the bulk entanglement piece. So far we can see these order n terms, or 1 over g string terms, in this Fermion model, but it'd be nice to see, can they be captured by the string description without doing the full sum over all topologies and analytically continuing? And I think there are some other models that would be interesting to consider, for example, in the context of ADS3 CFG2, to start looking at holographic models. Okay, so thank you.
Questions?
Quick question, actually. Well, do you see any of these being sort of interesting in the context of like SYK and JT gravity, in terms of either seeing these sort of like different scaling or?
Yeah. So good. I think that would be. I think that'd be a very interesting thing to consider. It's basically what this is it's sort of like it's what you would expect kind of to. Well, the way people think about SYK is usually you take some low energy limit, you describe Schwarzian quantum mechanics, and then you describe its dual as some gravity theory. But here this is more like what you would expect from a bulk dual of something which really had the microscopic degrees of freedom in it.
By the
Yeah.
start.
Exactly. So there are some, I think it would be interesting to consider there's some models that are very closely related to this 2D Yang Mills that would be interesting to look at. I don't know if you could do SYK exactly with this kind of. I don't know exactly what the string, how one would start building a string dual to that. But yeah, I think there are probably models in this neighborhood that we could consider.
Yeah. So let's make Wu again.